All right, so today we are gonna talk about ethers and epoxides, even though I was supposed to cover this with alcohols. I just kind of figured like 10 mechanisms was too much for you guys. Um, all right, so let's just kind of pick up where we left off from alcohols. Essentially, why I put ethers with alcohols is because making ether is a form of an alcohol reaction, right? And what you always would see is that when we talk about the Williamson ether synthesis, we have a starting material that's always an alcohol, okay, with a strong base. And of course, you need an electrophile with a good leaving group, right? Combine all of that together, you are going to get an ether, okay? So let's look at some examples. I have this here. Okay, and a strong base is usually in the form of sodium hydride. This is not my first choice. I don't really like using this just because of personal preference, but feel free to just stick with this if you're already comfortable, right? So I have an alcohol right here, strong base, electrophile, and leaving group, right? So together they are gonna give me this product here. Okay, and for another example, if I give you this, right? Another strong base or a set of reagents that we usually use, and this is what I really prefer. You would see me using this as the default for all the retro problems I'm going to write for this semester. It's potassium hydride in 18 crown 6, which I'm going to explain a little bit more. And then all these are done in the presence of THF. And then if I had, let's say, ethyl iodide, what I'm going to get is this here. And of course, I will be talking about the mechanism in just a little bit. Okay, so what are crown ethers? Every time if you see a number, crown number, right, it denotes a crown ether. And it's a really good solvent, especially for 18 crown 6, where it sequesters potassium ion or solvates it. So remember why we use polar aprotic solvents, because we want to capture the counter ion. 18 crown 6 is really good at doing that with potassium, as with 15 crown 5 with sodium. So 18 crown 6 looks like this. Okay, and it perfectly holds the potassium ion here, okay? Or if you have 15 crown 5, then it would be this here. And it solvates sodium. Okay, so 18 crown 6, potassium, 15 crown 5, sodium. Okay, it's unique like that because of its large internal cavity that you see here. So therefore, the potassium ion is able to go in there perfectly. Okay, don't forget bases are not limited to just sodium hydride or potassium hydride with 18 crown 6. You might see other bases such as butyl lithium compounds. Remember when we discussed alcohols? And butyl lithium is a really strong base. It deprotonates any acidic hydrogens, and this is exactly what it's going to do. Okay, you might have seen LDA as well. Probably when you were making alkynes. So LDA is going to be on a strong base. Grignard reagents could possibly serve as a strong base as well. Because remember, Grignard reagents are reagent alcoholic, so it finds the most acidic proton here, right? And then, of course, everyone's favorite in alkynes, sodium amide. That is also a possibility. But the most common ones that you might see are sodium hydride or potassium hydride in 18 crown 6. Okay, so let's look at an example again. I'm going to show the mechanism. Okay, I have this molecule here. Okay, and I'm going to use potassium hydride in 18 crown 6 and THF, and then followed by ethylite. Okay, and what I'm going to get is this here. Okay, methyl. So let's look at the mechanism. Okay, I have my starting material, right, with a strong base. So remember, when you have hydrogen attached to a metal, hydrogen is negatively charged. So it's going to function as a base, okay? And what it's going to do is that it's going to go and grab the most acidic proton here. So what you have is now a deprotonated oxygen atom, and this is really, really nucleophilic, right? So what do nucleophiles do? What's the role of a nucleophile? Attack? No, it does not attack the leaving group. It attacks the electrophile and kicks off the leaving group, okay? This is why I need you guys to interact, because when you tell me stuff like attack leaving group, I can call you out on your mistake so you don't push the wrong things out of the molecule. Right, so we are going to find the electrophile with the leaving group. So ethyl is the electrophile, bromine gets kicked off, right? And this is how we form our product. Okay, it's really simple, as you can see. Straightforward, not too complicated. If you have this as a mechanism question, which I honestly highly doubt you would, well, just thank the giant turkey up there. Okay, there is something that is a little gray. I don't quite like seeing this because, well, this is more for an Orgo 2 problem, but technically on carboxylic acids, if you run the same reaction conditions, right, you technically can make this product here, although there is a better way called the Fischer esterification, which is going to be covered next semester. So this year, it technically works. Okay, but Fischer esterification is preferred. And I'm not going to talk about it at all. Next semester, maybe. So don't worry about dealing with carboxylic acids. But just in case you do, count them. All right, so there are more stuff that we can talk about, such as, okay, now synthesis strategies. When it comes to synthesis, you have to be careful. Okay, why? Because let's look at this molecule here. Okay, can anyone tell me what the difference between two functional groups on the benzene ring are? One is an ester and one is a ketone. Exactly, right? So say I wanted to make this compound here. Okay. Right? If I wanted to make this compound, I see that I have an ether right here, but nothing changed over here, right? So can I use LiAlH4? Can I use lithium aluminum hydride to reduce the ketone into an alcohol in this case? What would happen if I use lithium aluminum hydride? Can someone tell me what would happen to the ester? Yeah, exactly. When you use LAH, it's a strong reducing agent. You're gonna knock the ester down into a primary alcohol again, and what you want to get is two equivalents of your cyclopentane. And that's not what you want, right? You just want the cyclopentane to attach to the ketone, to the alcohol that was originally a ketone. So what reducing agent are we going to use here? No, because don't forget Grignards, you are attaching the R group onto the carbon containing the alcohol, right? So it's not a Grignard, but yes, Songwoo, you're exactly right. You're going to use sodium borohydride in methanol. Please don't forget the methanol part. And then second step, we are going to do a Williamson ether synthesis, which is potassium hydride and 18 crown 6 THF, and then bromocyclopentane, right? Or iodine, any good leaving group basically. You might see OTMS. That's fine as well. Okay. Just realized I gave you the template already. Never mind. We can always keep that for later. All right. Let's work at the next example. Let me just write here. The order matters. Okay. So right here, I have this starting material, and I am making this here. Let me see. Okay, so I am attaching a benzyl group on this side of the molecule, right? I have a benzyl group here, and I have a methyl group here. See? So in this case right here, what do you think we should be adding first? Should we be adding the benzyl first, or should we be adding the methyl first? Yeah, we should be adding the benzyl first, right? Because we know that the benzyl stems off the ketone, right? So we can use milder reducing agents without reducing down the ester. But if we use lithium aluminum hydride and did the ester first, everything is going to get knocked down to an alcohol. And if we put methyl into the Williamson ether synthesis, this is not going to be benzyl, it's going to be methyl, right? And that's not what we want. We want it to be methyl and benzyl on the ester and ketone respectively. So what are we're going to have to reduce down the ketone first using milder conditions. So you're going to use sodium borohydride in methanol. On step 2, you're going to use benzoyl bromide or benzoyl iodide is fine. Sorry. Before that, you're going to use a strong base to deprotonate the hydrogen first. Okay, so let me draw the steps here. So once you reduce it down, you will get this, right? Because lithium aluminum hydride has no effect on esters, but it has an effect on ketones. So after that, we can do our Williamson ether synthesis to put benzoyl, right? So benzoyl bromide, before that, I keep forgetting. Strong base. So I'm going to use the usual benzoyl bromide to give me this here. So I have my benzoyl attached. And my ester remains intact. Okay, then what am I going to do next? I'm going to have to reduce my ester into an alcohol, right? And then from an alcohol, I'm going to work it up to an ether. So what reagent am I going to use now to work this ester down into, this ester down into a primary alcohol here? What reagents am I missing? Good. Lithium aluminum hydride in the presence of what? Water? Or, are you sure? In the presence of THF or diethyl ether. And then you do an acidic workup with water. Okay. Seems like I need more space, so let's strip this down. Step 5, you're going to conduct the ether synthesis here, right? And you're going to use a strong base. So sure, go ahead and use the same thing. And this time you're going to add methyl bromide or methyl iodide. Okay, so this is how you would synthetically go about getting the final product. So remember, I'm going to ask you now what happens if you use, so this is just something to remind yourself. What happens when you use LiAlH4 in the first step? Okay, so I'm writing this here so that when you revise or when you study it, you can ask yourself the same question and make sure you know why we're not using lithium aluminum hydride in the first step. Okay, one thing is that you really need to take into account is that this Williamson ether synthesis process is an SN2 reaction mechanism. Okay, it proceeds with via a backside attack. I hope you guys remember what that is. It's important that you identify, because I'm going to go through an example later where you cannot make something with Williamson ether. You cannot make a certain ether with Williamson ether synthesis because it fails the SN2 part. Okay, so what you're going to need is a primary R group attached to a halogen or a good leaving group, because what would happen if we had, let's say, a tertiary substrate? Can someone guess? So let me put it this way. If you guys have my table from exam 2, that is where you want to gonna look at for the answer. If I had this, right, versus if I had tert-butyl. Are you sure it's SN1? So my nucleophile attacks, no. under strong basic conditions, remember, which means that technically I can also add Naomi here. What would happen here? Are you sure? No, it's not going to attack, but rather it's going to give an E2 reaction mechanism. So tertiary substrates, right, they will favor E2 instead of SN2. And your reaction will fail. Okay. And then when you design, I'm going to explain in detail later, but when you design or when designing synthesis processes, okay, we want the R group to the leaving group to be as less substituted as possible. Okay, so remember, increasing rate of SN2 reactions, primary is the strongest, secondary, tertiary. So technically at tertiary, we kind of not have anything going on here. Okay, so remember, if it's an SN2, it's a backside attack. And therefore, stereochemistry is important. I hope you guys know what to do if you had a substrate that has chiral centers with them. I hope you guys know to flip them when necessary. Okay, so I'm going to give you an example. Okay, can this be made by Williamson ether synthesis? Okay, so it's this one here. Okay, can someone tell me, is it possible to make this using Williamson ether? Yeah, exactly. We can, right? Just kind of gave you the answer beforehand already. So this one right here, this substrate right here comes from this. Sorry. If it comes from this, what happens? No SN2, right? You're gonna get an E2 instead, so that's not gonna happen. What about this here? What's wrong with this substrate? It's an sp2. And can sp2 molecules go through SN2 reactions? No. Okay, so there's no way you can make this yet, at least for as far as I'm concerned for you. You don't need to know how to make this. It's just not possible with the Williamson ether synthesis. Okay, and with that, we are done with ethers. As you can see, it's a really simple process, but I'm going to use ethers to show you how we can make epoxides now. Okay, so let's talk about preparation of epoxides. Let me just get that open. Okay, so epoxides. Who here remembers one of what reagent we're going to use with an alkene? MCPA in dichloromethane. Excellent. Okay, so in case you okay, let me just draw out what's happening here. So I have alkene, I have MCPBA, dichloromethane. When we taught you addition reactions, right? We just made it. We told you that, oh, this kind of gives you the anti-dihydroxylation plus the enantiomer here. right? But then the dihydroxylation part comes after you make the epoxide. So I feel like I just need to remind you again, MCPBA means meta chlorobenzodic acid. Okay, and it looks like this. Okay, and this is the hydrogen that's really important here, because this is the hydrogen that they're going to give up onto the alkene. Okay, so let's look at it proceeds via a considered mechanism. In an SN2 process. So let's look at the mechanism. So this molecule is neutral. There is no plus charges anywhere whatsoever. Okay, so who here, I hope you guys can remember the mechanism from when we taught you in alkene additions, right? This is how you would do it. So, okay. All right. The alkene is gonna attack the alcohol. Sorry, not the alcohol, the oxygen, right? And then this bond is gonna be broken. Okay. Once this bond is broken, this happens here, but I'm not gonna put it into the mechanism here. So essentially, this has sort of like a temporary negative charge, but as soon as it hits that, it's gonna grab this proton here. Okay, and then now this here is now his turn to be temporarily negatively charged and really nucleophilic. So this part is going to be temporarily electrophilic, but because this is a concerted mechanism, it's going to go here. Okay, and then we hit the transition state. Now, how do we know what to draw for transition states? Whatever that's breaking being made becomes a dash line. Okay, so H O O. Okay, remember dash lines? Because I'm making this bond and I'm breaking the double bond here. I was breaking this bond off and breaking this bond off here, right? At the same time, this oxygen now, where I'm drawing from, is going to create a double bond with, it's going to create a bond with the hydrogen there, as a hydrogen's bond to the original oxygen is broken. Okay, and what do we call this transition state? Anyone remembers? It has the name of an animal. Yeah, it's a butterfly transition state. Okay, if you are asked to draw the mechanism, you need to know how this transition state looks like. Okay, and then after it forms the transition state, you can just put product. This is how the product just forms. Okay, the other way that an epoxide can be formed, okay, this is the less conventional way, but it's still kind of, it might be in your problem set, okay, is with an Williamson ether synthesis. Okay, so for example, if I had, it's a combination of reactions actually. It's first you're gonna have the halohydrin reaction. Okay, the halohydrin forms, and then you're going to use Williamson ether synthesis. How? So let's see here. If I had this starting material, for example, okay, and I treated that with water, sorry, bromine and water. Okay, I will get the alcohol and sorry, the hydroxy group and the hydrogen on the carbon chain, right? So now, do you notice this? These were the conditions for Williamson ether synthesis. You have an alcohol, you have an electrophile here, and you have the leaving group here, right? So all you need to do is just treat it with a strong base. And what happens as a result is you get an epoxide. Okay. This is called the intramolecular SN2 reaction. Intramolecular SN2. Okay, and it's important that you take note if you have such a question or if you see a question like that on the problem set. The leaving group must be anti-periplanar. I hope you guys also remember what this means. Okay, and what must it be anti-periplanar to? It has to be anti-periplanar to the oxygen. So let's look at an example. Okay, I have this and this here and the isopropyl here. Okay, so whenever you have something like that, the first, can you tell if there's any interaction here by looking at it on the 2D plane? Not really, right? It doesn't look as accurate. So what would be better is if we converted that structure into a chair. So take it as I'm killing two birds with one stone right now, that I'm going through some of the final exam stuff, teaching how to draw chairs. And what you want to do is to draw this right here. Okay, so this is the alcohol, and this bromine. Hang on, let me see if that works better. Give me 1 second. Okay, yeah, and then you have your isopropyl here. Okay, so let me just label my substituents. Alcohol is right here. Bromine is here. Okay, and then the isopropyl group is right here. Okay, now, with that being said, I can see that my hydrogens here, right? They are sort of like anti-periplanar. Here, right? This whole part here is anti-periplanar. You don't need to know the Newman for chairs, but suffice to say, technically, if they're on the same side, then what happens is that if when my base attacks the hydrogen, the oxygen that's sticking out is able to reach to the electrophile and kick off the leaving group. Okay, because of the way that the molecule is formed. So we see that oxygen is kind of pointing down. So what we get is this here. Okay, so essentially we're going to get this epoxide with isopropyl, and if we convert back into a 2D cyclic chain, nothing changes, right? With the isopropyl, so it still remains a wedge. But then now you know this is going to be right here. Okay, so this is one example, but I'm not, like I said, I'm not going to go through too much in detail because you really don't need to know this, but just in case. And if you encounter this in your exam, or sorry, encounter this in your problem set, it's similar to why I covered strong bases, alkyl lithium reagents. You might not see it in an exam, but there is one question in your problem set which makes it fair game. So it's always better to be safe than sorry, right? Okay, what if you had something linear? Let's try with something linear, such as this here. Okay, and if you use a strong base, such as, well, let's just use NaH and DMF. Okay, are you gonna get, what kind of product are you gonna get? We don't know, right? And how are we able to represent this? Well, here we go again. Take it as a final exam review. Anyone has a hint of what I'm drawing? With a circle, something with chiral centers? Yes, you are talking about a Newman projection, right? Because remember when we talked about E2 reactions, when the leaving group has to be anti-periplanar, we draw Newman projections to show us exactly what's going on first, right? So where are we going to draw off the Newman at? Well, it's going to be off here. So alcohol is facing out, right? What else do we have? We have the propyl group at the bottom. And then we have hydrogen pointing off to the left here, right? Okay, and then at the back, what we have is bromine that's at the facing out in the back, and then we have an ethyl group at the top, followed by a hydrogen. That's here. So again, remember Newman projections are arbitrary. If my way of drawing Newman projections is that if it's a wedge, right, I have it pointing out to the right. If it's a dash, I have it pointing at the left of the Newman projection. Okay, and that's just my way. If you go on the other, if you choose to do your own convention, you have to stick with that and be consistent, and you will always get the right answer. Okay, my way is just the kind of like the cheat way because I'm really conservative like that, right? At the top, yes, actually at the top is methyl, not ethyl. Sorry, good catch. Okay, so when I deprotonate this hydrogen here, I'm gonna write it in Greek so that you guys know it's deprotonated at the end. Okay, is my resulting oxygen anti-periplanar to the leaving group? It is, right? You can see that it's anti-periplanar, so it's gonna attack the electrophile and pick off the leaving group. And what we get as a result is, well, this product here. Okay, you don't have to invert anything, so that's fine. I'm not going to talk about, well, technically because this is a transalkane with an epoxide, you can also express it like that. You might see this in your answer, but it really doesn't matter if in what way you express it. Okay, just be the crux of this whole thing is just to make sure that your leaving group is anti-periplanar to the oxygen. If it's not, rotate it until you get it to be anti-periplanar, and then do the deprotonation. So you should be able to handle it from there. Okay. All right, let's talk about opening reactions. So epoxides are now a third way of elongating a chain because, well, if you look at an epoxide, I have a site here that I can attack, and I have a site here that I can attack, right? So I can technically make stuff like that, just from an epoxide. So it's the first way you guys learn how to make a chain longer for retrosynthesis is what? Alkynes. Okay, and then just on Thursday, I taught you another way, right? My friend with a drinking problem, what's his name? Yeah, Grignard reagents. You can also make a chain longer with Grignard reagents, and now you're going to learn a third way for retrosynthesis, and that's through epoxidation. Okay, so epoxides behave differently under acidic conditions as well as basic conditions. You have to be really careful when you see your reagents, okay? Your reagents are going to tell you what kind of conditions the reaction is going to be taking part in. If it's basic conditions, okay, let me just write here, epoxide opening under basic conditions. Use a different color for that. Okay, if you're using under a Grignard under, an epoxide under basic conditions, what dominates this reaction mechanism would be sterics. Okay, so for example, if you see Grignards, you can open it with Grignard reagents, or you can open it with any polar aprotic solvent. With such as NaR, right? Kr, where such as for example sodium cyanide, it's one of them. Yes, H, NaN3, KCN, so on and so forth. You guys get the idea, right? So when you see like SN2 type of reaction conditions, what you want to do is to know that it's going to open up under a basic condition. So let's look at an example. If I have this here with epoxide, okay, and for example, if I use sodium azide in DMF, okay, and then I do an acidic workup, such as water with H plus, or you might see NH4Cl. It just gives you a hydrogen atom basically. What you get as a result would be this. Okay, and it might not make sense right now, but let's look at the mechanism so that you can understand why we get that product. Okay, so the mechanism, okay, let me just write this here. Sterics dominate. Okay, when the steric conditions, the nucleophile is going to attack from the least substituted site. And that's why we get the product that I just drew here. Okay, so I'm going to draw the mechanism so that we can understand why we have that. Okay, so first things first, my nucleophile is the azide anion. And remember, when sterics dominate, right here, sterics dominate. So least substituted site. We're here, I'm sure you guys know at this point of your orgo career, you should know what the least substituted site means. It's going to come here, and it's going to break open the ring. Okay, so SN2, this is where it occurs. Did SN2 occur right here, the one I circled? No. So should I leave the stereochemistry alone or should I invert it? Exactly. You should leave it because the stereochemistry SN2 did not occur at the spot where I circled it. Everything remains as it is. You are going to flip this stereochemistry here through the azide ion, right? So what you have is this here. So because SN2 did not occur here, you just leave it as it is. Now you have oxygen here. And what would be the stereochemistry of my azide? Should it be a wedge or should it be dash? Good, because this is where backside attack occurred. So it came from the back. And then, so this is step 1. And then step 2, when you do an acidic workup, in comes in your acid, right? So your hydrogen. And this is just where, kind of make the product complete. Right here, and there we go. Okay, so this is what happens under basic conditions when sterics are a dominant factor. Okay, and then we can talk about opening epoxides under acidic conditions. Anyone here has a clue or a hint of what I'm gonna go to when I'm talking about acidic conditions? What kind of solvent are we looking at? So we need an acid for sure, but typically what kind of solvent are you gonna see? We use polar aprotic solvent for basic conditions, right? What about acidic? We're going to use polar what? Protic solvents, exactly. Can someone give me an example of a polar protic solvent? Are you sure DMSO is a polar protic solvent? That's a polar aprotic solvent. So water is going to be polar protic. HCl, ethanol, methanol, any thiols are going to be okay. So stuff like water, any R group with an alcohol functional group in it, right? Any R group as a thiol, and all these takes place in the presence of H plus. Okay, so you have to be careful. If you see, for example, ETSH, for example, you're adding the thiol there, ethyl thiol. Okay, please take note. These are signs that tell you that the epoxide is going to be open under acidic conditions. And when we talk about acidic conditions, okay, the mechanism is going to be a little bit different. So if we had this here, right? And I said I'm adding isopropanol with H2SO4. What I'm going to get is this product here. Okay, and of course, with every reaction that we talk about, let's look at the mechanism. Okay, so we have this here, right? And the first thing that it's going to do is to find the acid, right? Because under acidic conditions, the epoxide now becomes a nucleophile, and given its lone pair ratio, is able to grab a proton. Okay. And we have this here. So now, does this look familiar here? You have a bridge to an atom with a positive charge. Where have you seen something like that before? Where is it analogous to? You have seen this in two other reactions. One is oxymercuration, right? The other one is the halogen formation. You have the bridgehead going to the atom with a positive charge, and this is exactly what happens. I remember we told you that you always go and attack the more substituted site as a result. This is exactly one of the cases that's really similar. So right now, if I'm adding isopropanol, okay, remember isopropanol comes in as a whole chunk and attacks this right here. Okay, let me just write a note there that under these conditions, electronics dominate. Okay, because this site here is more electrophilic than this site, so it's gonna get attacked on the more substituted site. Okay, and then when that happens, you break open the epoxide chain, basically. Let me just show you break this open. So now you have an OH here, and you have OIPR and the H atom. Okay, and how you're gonna get rid of the hydrogen is just another way of, you can just use another starting material. Right? Which comes and grabs this, and then it just carries on. So yes, this is exactly like a MCPBA opening reaction that you've learned when we talked about the diol formation, right? It attacks the more substituted site, and this is exactly what happens here. Okay, let me see. Okay, I just want to draw your attention real quick to the textbook. If you guys are textbook users, here is what the textbook says. And okay, the textbook says that only under primary and secondary substituted epoxide conditions would it be in the least substituted site, and only in tertiary site would it be the more substituted. Basically, it will attack the more substituted site, and this is wrong. Okay, because the book kind of splits it into two different categories, and that is not what really happens. It's always under acidic conditions that the nucleophile will attack the more substituted site, regardless if it's primary, secondary, or tertiary. So if you're a person that follows the book really closely, please take note of that. All right. Yeah, that's all I have to say with regards to the textbook, because that's a really glaring mistake there. Okay, so let's essentially this is all you need to know for epoxides. I will probably go through like a few examples just to maybe to 8 o'clock, and we'll call it a day today. Today is just gonna be one of the easier days. We are not gonna spend too much time on material, because this is essentially the last chapter, which is the last thing you need to know for your exams. So please give it some attention as well. The last problem set has N-butyl lithium. I saw that. So for example, let me just remind you what happens with N-butyl lithium under epoxides, or rather alkyl lithium compounds. Okay. The ring, or rather the epoxide, is open via an E2 reaction. So let's look at some examples here. One example rather. Okay, say I had this, right? Okay, and I had N-butyllithium in THF, and then I do an acidic workup. Okay, what you might think what you might think happens is probably, oh, N-butyllithium, strong base, right? You might think that this ends up happening, but this is wrong. This does not happen. Okay, what really happens? Let's look at the mechanism. Because you are using strong alkyl lithium compounds, it will be an E2 reaction mechanism instead. Okay, so N-butyllithium is going to deprotonate the most acidic proton. And the most acidic proton is the one that is adjacent to the epoxide, okay, which is right here. This is where your most acidic proton is. And bases, remember, I talked about nucleophiles finding electrophiles. What happens is bases, they find the most acidic proton. So when you eliminate this hydrogen here, you get a double bond that's formed, and then this in turn opens up the epoxide ring, leaving you with this. Okay, and then you have a double bond here. This is just specific for N-butyllithium. If you had a Grignard reagent, then basic conditions apply. Okay, so just take note. And then when you do your acidic workup, everything just goes the same from here. Okay, so what you have essentially for your real product is this here. Okay, and this is the correct one. Any questions on that? So this is specific to lithium compounds. When you see alkyl halides, okay, with lithium on it, then you are gonna encounter this situation. Okay, but if you had a Grignard, for example, they just follow basic conditions. Okay, so for example, if I had this here, right? And if I use a Grignard, such as methyl magnesium bromide, diethyl ether, and then water or H3O plus, then what happens is that the methyl is going to act as a nucleophile and attack the least substituted site, opening up the ring to give me this intermediate here. Remember, SN2 did not occur at the top, so that remains the same. And then methyl is going to come in from the back, right? And then I do an acidic workup. To depronate this atom here, and then what I get as a result would be this. Okay, so as you can see, they behave the same way as so if I put NaCH3, for example, stuff like that, you technically can have the same thing. Okay, but remember, so Grignard don't exhibit this behavior as we see in alcohols, but for N-butyl they always function like that. Okay. All right, and then we'll work on some examples now. Okay, let me pull out my examples, and then you guys can take some time to copy this down. Okay. Okay, let's try an example. Not necessarily with epoxides, but more of alcohols. I just want to see how you guys are faring at this point. Okay, let's try with this here. All right, first and foremost, what question is this? Is this a predicting the reagents type of question, or is this a retrosynthesis question? How do you know? Say someone just signed up for Orgo today. How would you tell him this is a retrosynthetic arrow? Good. The double arrow. It tells you that, yeah, you're having a thick arrow, so it's retrosynthesis. Where is my product? Where is my starting material? It's really encouraging to see that you guys remember starting material, product. Right? We're gonna work our way backwards. So, what are some of your thought processes here? You have an R group, right? But there are many ways that you can attach an R group now, right? You have alkynes, you have granular reactions, and you have epoxides. So we have to figure out which one we're going to use. And we're going to see, based on our end product, right, it will give us a clue to what really happens. So, okay, let's see. What else can we talk about? We have a ketone as the final product. So we know that we need to work it up. Okay, and so when we work up stuff, we are gonna have an oxidizing agent of some sorts. By the way, did you guys learn this thing called Tempo or Des Martin Peridot Ionane or whatever it's called, DMP? Did you guys learn these as oxidizing agents? Okay, so since you guys didn't mention that, since you guys were not taught that, I'm not gonna mention those. But even if I did, they're just basically two different other ways where you can work up an alcohol into a ketone or an aldehyde, but you don't need to know the mechanism for that. It's in your book, by the way. Okay, can anyone else tell me what's important about this reaction? Can I just dive right into the reaction straight away? Hint, if I am having one of these conditions, my alcoholic friend is probably going to come to the party, right? What do we need to do? We need to hide the alcohol from him. How do we do that? We protect it. Okay, so first things first, always remember that you're going to work off with trimethyl silyl chloride, and that's exactly what we're going to do. The first step here. So let me draw the pathway. Well, Mariah, you could go forwards, you could go backwards. It really doesn't matter. For this, I am just gonna go backwards just to show you what a true retrosynthetic question would kind of look like and how you should approach it. You can technically approach all retrosynthesis questions backwards, but sometimes going forwards might be a little bit harder, okay? So I know that my previous step, I have my alcohol that's still protected, so it was still being TMSO state. And I say that, okay, because I have a ketone, I know it needs to be worked up. So it has to be an alcohol here, right? With my new phenyl group. And then this, before that, well, oh look, am I getting closer to the starting material? Actually, I am, right? This is right here. And then back to the starting material. Are you able to tell me how can we piece them together now? Okay, so all together, okay, so let me draw one. What would be step one? You need to protect it first. In the presence of what? Water? DMF? Pyridine. Good. You can just write PY and you'll get the full credit. Okay, step two. So let me just be consistent with the colors. So first step, you need to protect it. And step two, you're attaching an R group, right? So what are you going to add? You're attaching a phenyl group. So it would have to be phenyl, magnesium bromide in the presence of good. THF or diethyl ether, and then step three, you have an acidic workup. So you have an alcohol. And then what's step four? You can use any oxidizing that you like. What are you gonna choose tonight? What are some of those stuff that you guys are already familiar with? PCC, PDC, sure, PCC, PDC, CERN. I can use, can I use Jones here? Can I use any chromic compounds here? What would happen if I use Jones reagent? Yes, exactly. You have a carboxylic acid because this here gives a source of hydrogen, which the Jones reagent is going to cleave off the entire thing and give you a carboxylic acid. And that's not what we want, right? So you cannot use Jones. But sure, PCC, PDC, SWERN, all in the presence of pyridine. I mean, if you choose, let's just put PCC or PDC in the presence of pyridine. That way it's a little bit easier. And then step five, is there a step five? That's required or no? What's step five then? The color should be a hint. You have to exactly deprotect the alcohol using TBEF and triethylamine or pyridine. That's fine. Okay, I need you guys to get used to the idea of um, of putting Grignard reagents as something that you can predict the reagents with, because not many people have issues with, not many people are able to see that. So make sure you do enough practice to know what's going on, okay? Instead of TBEF, you could also use cesium fluoride. That's also a way that you can deprotect. I don't want to be either, that's fine. I don't know if you guys were taught cesium fluoride, but if you weren't, then don't worry about it. All right, let's look at next example. So I have this here, and then Okay, so if you were asked to perform a retrosynthetic analysis on this here, I'll tell you what, I'm gonna go ahead and give you 5 minutes. Think about it. Use the chat box to discuss and use it as a think tank, and I will come back and we'll see how it goes. Okay, so yeah, go ahead. All right, anyone has any thoughts? Do I've been doing from the previous example? So you have, okay, what you have here, you have an alkene, and you need to make a chain longer, right? Alkene to make a chain longer. That kind of gives you a hint, right? Whenever you see alkene, this guy comes out to play. You have to put in epoxide, probably. What else? Do I need to oxidize anything at any point? Yeah, right? At some point, okay. Um, so I have also, okay. Also, how many more carbons am I adding? 2. 2 more C. 2 more C. Okay, and now since we know we're going to use an epoxide, are we going to use it under basic conditions or acidic conditions? The hint lies with this here, right? Since R group attachment is a terminal R group attachment, you are going to use a basic condition. Okay, I will show you what happens if you attempted the acidic route. Okay, so altogether, what's the first step? How can I make an epoxide from an alkene? You're going to use MCPBA in the presence of dichloromethane. So this way I'm showing you the forward route from here. Okay, and I'll draw the product of each reaction that comes out of it. Okay, so we have an epoxide now. And this is why it's important that you need to know we're going to use basic conditions. And since we're adding 2 carbons, well, ethyl magnesium bromide, right? It's gonna come and attack the least substituted site and open up the ring. So ethyl, magnesium, bromide, and THF, H3O plus, right? And what I get as a result is this here, correct? And then I can oxidize it into my final product. So I'm just going to use PCC and purity to give me this here. And there we go. It's not that hard, right? Okay, so let's see what happens if we used an acidic product. So if I had ethanol in H plus, for example, right? Because we know we're adding 2 carbons. What happens here is that the epoxide, so everything I'm drawing in gray is going to be wrong. It's going to deprotonate this hydrogen first, right? And then it's going to have this intermediate here. After the nucleophilic attack, I'm just going to skip steps. You're going to have this, and you're going to have this here, right? And is there any way you can oxidize it? No, right? Because this is already an ether, it's unreactive. And second, the ethyl is not on the right placement. If you oxidize this, what would happen? Instead of getting a ketone, you're going to get an aldehyde here with an ether. So the epoxy group, and then you're going to end up with an aldehyde. So this is wrong. Okay, so this is if you are confused between acidic and basic conditions, this is what you're going to do. Try both. See which one gets you the right answer, because one has to get you there. If you are doing it wrong, if you get both wrong, then something is not right with your mechanisms. Okay, steps 2 and 3, OH goes on the, technically, no, it ends up on the more substituted site because your nucleophile attacked from the least substituted site. Right, so you see, this is secondary, this is primary. Where did your alcohol end up on the secondary position? So it's on the more substituted site. But I don't like using that because it just confuses people. I prefer teaching it with the where the nucleophile is going to attack from. That gives a better yeah, okay. So, well, if you want to know how is it basic or acidic, like I said, usually internal, like more substituted alcohols, then you know you're working with basic. If it's less substituted alcohols, especially if you have an ether as a result of it, right? You are gonna have more acidic conditions. But as you're starting to pick the material out right now, the only way you can go about really seeing it is by practicing. So you need to do a lot of practice. I did give you a retrosynthesis problem with epoxides. It's titled NMR number 10. So for those of you who have been following my worksheets for the past 10 weeks, while 8, 9, and 10 are up, I'm gonna go through all the solutions on on Wednesday at my review. Okay. I will be posting answers to those as well, but probably after I go through them. If you are taking the exam before and you need them, just let me know. Shoot me an email and I will reply you through there. All right, with that, this kind of brings me to the end of my last content review with you guys. Next time I see you guys would be for the final. If you're registered for it, please take note. I might be canceling my Monday morning office hours because I literally have no one registering for that. So I will continue with the 8:30 one, but as far as the morning is concerned, I will not be hosting them anymore. Okay. Depending on the situation on Monday, I might just end up being at the MSLC at 9 a.m. And if I do, you guys can find me there. If I don't, then I'm sure there are probably going to be other peer leaders as well throughout the week. Okay. So for those who register, the morning one, I will automatically include you in the evening registration. Please take note that when you register for the final, you have that you register for the right session. Okay, don't see the word retrosynthesis and get excited and then just go and register for that, because that retrosynthesis is for Orgo 2. So if you want to do Orgo 2 retrosynthesis problems, you are more than welcome to do that. Uh, Feel free to join us at 7:30. Okay. I've already kind of yelled at a few people because that really adds onto my workload. If you register wrongly, please don't do that. Okay. Um, have some thought for me. Just be careful when you register. And yeah, this lecture capture will be going on YouTube right after I close off the room. So expect a link by probably 9 p.m. I'm gonna need some time to process this video. Thank you for behaving. This is your reward. See, this is what happens when you cooperate. And yeah, if not, then I will see you guys along the week. If I don't see you, then all the best for your exam. You guys have been fun to teach with. I'm gonna miss you guys. I hope I can follow up to Orgo 2 next year. And yeah, we'll have more fun then. Orgo 2 reactions are a lot more interesting.